So I hope you got the clear-cut understanding about z-test. So now let's take a simple example and try to understand this better. So in this case, the problem statement that we have here is, suppose you work for a company that manufactures light bulbs. The company claims that the average lifespan of their light bulbs is 1000 hours. However, you want to investigate whether the average lifespan is significantly different from this claim. So this is what the problem statement. Let's begin with the step one. Always the step one is state the null hypothesis and alternative hypothesis. So the null hypothesis, which is H0, assumes that the average lifespan of the light bulbs is 1000 hours. The alternative hypothesis H sub A assumes that the average lifespan is different from 1000 hours. So this is what the null hypothesis and alternate hypothesis that we have here. So let me write it down. So step one is to write down the null hypothesis and alternative hypothesis, and that's what. So let me say H0, which is the average lifespan of the light bulbs is 1000 hours. And HA, obviously it's not, is the average is different from 1000 hours. It could be high, it could be less, it doesn't matter. It's different from 1000 hours. That's what it says. Okay, so that's what is our step one. Now step two. So what's there for step two for us? Step two is to after studying the null hypothesis, now it's time to collect a sample and calculate the sample mean and standard deviation. So suppose you collect a random sample of 50 light bulbs and record their lifespans. The sample mean lifespan is calculated as a 1050 hours. So the sample standard deviation is 100 hours. So that's what is the information here. So step two, let's get into the Jupyter notebook and let's try to do. So let me write down, let me start the walk. So B, let me import numpy as np, and from scipy import stats. These are the two things that are more than enough for me. So now let me bring down the data. So this is the sample data. I have collected the sample data. So sample collection and then measuring the lifespan, measured values of lifespan. Let me put it here. Absolutely fine. So now I have to calculate the sample mean and standard deviation. That's what next I have to do. So calculate the sample mean and standard deviation. So sample underscore mean is equal to np. Okay, here Let me check the data that we have. Is it okay? Let me convert that. Let me convert this into np.mean, and let me give the a list of data, and let me check, and I have to calculate. But before that, what I can do is, if okay, yep, let me directly print it here. Print sample mean. Okay, it's 1038.07, and let me go for the sample standard deviation, which is sample underscore np dot std. Yeah, let me give the data, and then let me print sample standard deviation, and here it is. So this is what the sample mean, and this is what is your standard deviation. Clear? Now let's get back to the walk. So that's what we have calculated the sample mean and sample standard deviation. Now it's step 3. So we have to determine the population mean under the null hypothesis. So in this case, the population mean is assumed to be 1000 hours. That's what we did. We said the population mean is 1000 hours because that's what it says, the null hypothesis. So the null hypothesis says the population mean is the average lifespan of the light bulbs is 1000 hours. So that's the reason for us the null hypothesis is sorry, for us the population mean is 1000 hours. Let me do that. Let me add that step. So let me say define the here itself. Let me say this place. Define the population mean under the null hypothesis. And here you can see the null hypothesis here itself. Yep, you can see that. So for me, the population underscore mean is equal to 1000. That's it. So now let me get back to the slide. Okay, what's next? So this is okay. Fourth step. Now all set, all done. Now it's time to calculate the z-score. So z-score measures how many standard deviations the sample mean is away from the population mean. That's what. So we have the population mean. Now we will be measuring how many standard deviations the sample mean is away from the population mean. So the formula for calculating this you can see on screen. So in this case, let's check the formula and let's do it. So from here, and let me print it and see z-score and execute. Okay, we got 7.64. This is actually huge. If you see your normal distribution curve in this shape, you see that my cursor moving, so it would be far, it would be away from this is positive 7.64. That's what the z-score you got, because at the center, if you see standard normal distribution curve, at the center you will have a mean of 0, and then positive 1, positive 2, positive 3, and it goes on. This side -1, -2, -3. That's how it looks, but we got a very high z-score. And now let's see what's going to happen next. So this calculating the z-score is done, and we got uh, whatever that you see on screen. So now So now we have to find the corresponding p-value. That's the fifth step. The z-score can be used to find the p-value, which represents the probability of observing a sample mean as extreme as the one obtained if the null hypothesis is true. So the p-value is determined using a standard normal distribution table or a statistical software. Here what we'll do is we will take the p-value using a library. So let me get back to the work here. Okay, so now it's time to calculate the p-value. So let's calculate. We have everything set. It's time to calculate p-value. So p underscore value. So I need to bring up some stats module. So that's stats. From stats, I have to say from stats library, I have to say norm, and then sf, which is sf, and inside that, if you want to just check stats.norm.sf, and inside you can give the information like 1 minus this is cdf, and if x is a given a random variable, that if it is a continuous random variable, then obviously we'll go for the density function. Okay, so what it will take, it will take array like quantiles, arg1, arg2, arg3. That's what it's going to take inside. So let me give that. So let me say absolute, because if it is negative also, I just want it as absolute z-score, and that too, it's on both sides. So it's a two-tail test basically, because what we are doing here, let me read our hypothesis one more time. Null hypothesis says the average lifespan of the light bulbs is 1000 hours, whereas alternate hypothesis says the average lifespan of the light bulb is different than 1000 hours. We are not worried whether it is greater or lesser. Alternate hypothesis, it says it could be lesser or greater. So that is the reason we have to take both tails. If you say only greater, then we have to take one type of tail. If you take only lesser, then we have to take another type of tail. But there it's a one tail test, but here it's a two tail test, because either way we are not worried whether it is greater than the null hypothesis or lesser than the null hypothesis. That's what is the point. Okay, so let me execute. So the p value has been calculated. Now let me check what's the value of p. So print p underscore value and execute. Okay, you got 2.0259 times 10 power minus 14. This number is pretty very small, absolutely small. So that's why you got, when you see that normal distribution curve, it would be out of the normal distribution curve somewhere. Okay, now let's get back to the slide. So now even you have calculated the p-value. So what's next? Now it's time to compare the p-value to the significance level. So the significance level, usually denoted as alpha, is predetermined and represents the threshold for deciding whether to reject the null hypothesis. A common significance level is 0.05. If the p-value is less than the significance level, we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So in this example, so let's look into our example. Obviously, we'll take up the significance value, and if it is lesser than that, we have to reject the null hypothesis. And that's what. Let's get back to our work now. Yeah. So now it's time to finish with this. So our last step is to compare p-value with significant level. So let me check a significance level is equal to 0.05. That's what we check. Normally it's alpha. So now if obviously you can see p-value is this much and significance is this much. With this you can tell. Anyway, let's use a code. So p-value, if it is lesser than significance level, so what it has to do, it has to print reject the null hypothesis, or else print fail fail to reject the null hypothesis. So if p-value is lesser than, that's what, if p-value is lesser than significance level, we can reject the null hypothesis. So let's execute and see what's the result we'll get. We have rejected the null hypothesis. That means what we can say is successfully is our population mean is not 1000 hours. It could be greater than that or it could be lesser than that, but it's not 1000 hours. So you can tell without doing z-test, but that is like your gut feeling. But when you do with this, when you tell with z-test, after doing the z-test, you can have a certain level of confidence. You have you will have a you will have a evidence or proof saying that this is the average lifespan of this bulb is not 1000. It could be more than that or lesser than that, with a significance level of this much, with a confidence interval of 95%, or with the significance level of this much, because that's what you said, because you have rejected the null hypothesis. That means you are saying that it's not 1000 hours. It could be more than that or it could be lesser than that. And that's what is your z test. So in layman's terms, this example is similar to conducting an experiment to see if the average lifespan of light bulbs produced by a company is different from what they claim. We collect a random sample of light bulbs and calculate the average lifespan. The z-test compares this sample average to be claimed average lifespan. If the difference is large enough that it's unlikely to occur by chance, so we reject the company's claim. If the difference could reasonably happen due to chance, we fail to reject the claim.